ladies and gentlemen, we welcome you all to attend the Future Ocean Forum today. I am Jianping Li, Dean of the Academy of Future Ocean AFO, Ocean University of China. It's my great pleasure, to co-host today's seminar with Professor Dong Lu, who is a PhD supervisor of the AFO. It's our great honor to have Professor Michael McPhaden from National Oceanic and Atmospheric Administration, NOAA. Before we commence, I would like to provide a brief introduction to Professor McPhaden. Professor Michael McPhaden is a senior scientist at NOAA's Pacific Marine Environmental Laboratory in Seattle, Washington. He is also a past president of the American Geophysical Union, AGU, a Nansen medalist of the European Geoscience Union, a Sverdrup medalist of the American Meteorological Society, AMS, and a fellow of the Oceanography Society, the AMS, and the AGU. For his contributions to assessments of the Intergovernmental Panel on Climate Change, IPCC, he shared the Nobel Peace Prize in 2007 with Gore and other IPCC participants. His research focused on large-scale tropical ocean dynamics, ocean-atmosphere interactions, and the ocean's role in climate. For the past 40 years, he has been involved in developing ocean observing systems for climate research and forecasting, most notable the tropical atmosphere ocean TOL, more buoy array in the Pacific for studies of El Niño and Southern Oscillation. He has already published over 300 articles in the peer-reviewed scientific literature, and is one of the most highly cited authors on the topic of El Niño. The topic of his presentation today is a year in the hothouse, El Niño, global warming, and 2023 climate extremes. This is a very, very interesting topic. Now, let's welcome Professor McPhaden to give us this seminar. Welcome, Professor McPhaden.
Thank you, Professor Lee, and thank you, Dong Lu, for the invitation to speak, and thank you all for joining us today. I'm going to share my screen now, and we'll hope that this works. I'm going to do my entire screen. So I'm going to talk about 2023 climate extremes and how global warming and El Niño contributed to them. And well, let's launch right into it. It is official. 2023 is the world's warmest year on record. In fact, the past 10 years have all been the warmest years on record, and we have not had a year below the 20th century average since 1976. And of course, this is all a signature of climate change. But if you look at the 2023 anomalies in the upper right here, you see also the signature of El Niño. And so the purpose of this presentation is going to be to discuss how the combined effects of El Niño and climate change have contributed to unprecedented high impact extreme events in the past year. And just to make this point early on, 2023, this is the global mean surface temperature record relative to the 20th century. The global mean surface temperatures in 2023 were 1.18 degrees Celsius above the 20th century average. And this smashed the record that was set in 2016 by 0.15 degrees Celsius. What these 2 years have in common, 2016 and 2023, is that they're both El Niño years. So the outline of what I'm going to discuss is here. I'm going to briefly highlight some of the extremes that have occurred in the past year. Certainly not all, there are many, but just a few to make the point. And then I'll talk a little bit about El Niño Southern Oscillation, or ENSO, dynamics and its global impacts. And then I'll spend most of the talk describing 3 ways that climate change and ENSO can interact to produce extremes like we've seen in the past year. So what are some of the extremes? Well, July 2023 turned out to be the hottest month ever recorded on the planet since 1880. The Northern Hemisphere summer is typically the warmest part of the year because there's more land mass in the Northern Hemisphere. But July 2023 was off the charts in terms of temperatures. And so this led to extreme heat waves in parts of North America, Asia, and Europe, resulting in many deaths from heat exposure. The oceans in the past year have been the warmest ever recorded. Every day since late March of 2023, the ocean set a new record for global average sea surface temperatures. And those records continue into 2024. In 2023, over 50% of the ocean experienced a marine heat wave at one time or another. And like on land, marine heat waves are very damaging to marine ecosystems and fisheries. Most organisms in the ocean live in a very narrow range of temperatures where they can thrive. And if the temperatures exceed that range, it can lead to very unhealthy ecosystems, mass mortality of fish and other animals in the ocean, and coral bleaching and die-offs. These are some of the global extremes. Some regional extremes. The Amazon basin is experiencing its worst drought in history. Stream flows are at lows not seen in the past century. It's been called an environmental, ecological, and humanitarian disaster. Because of the heat and the low stream flows, there have been mass die-offs of fish. Some of the tributaries of the Amazon have stopped producing hydropower, and many communities that depend on the Amazon for commerce and connection with the outside world have been cut off. And so it is a combination of climate change, El Niño, and also deforestation in this case. Some other extremes on the Horn of Africa. In late 2023, there were once in a century rainfalls and extreme flooding. In fact, there was 2 to 3 times normal rainfall in October to November 2023, and this led to hundreds of thousands of people being displaced and over 100 fatalities. Now, where I live in the Pacific Northwest, Washington State, we've also had some extremes. They're not as tragic as some of those that I've just mentioned, but it affects our economy. We have had a very low snowpack, and that's because of an unusually warm and dry winter. And this is going to affect us later in the year because this warm and dry winter meant that what precipitation oftentimes fell as rain rather than snow. And so it was not stored in the mountains for use later in the summer for agriculture, power generation, municipal drinking water, and salmon runs. So the fundamental cause for all of this is the constant rise in greenhouse gas concentrations in the atmosphere. We are presently at 50% above pre-industrial levels. We permanently passed the 400 part per million threshold about 10 years ago. And we've seen the highest carbon dioxide levels now anytime in the past 3.5 million years. And this is because of the human consumption of fossil fuels and the deforestation that pumps heat-trapping greenhouse gases into the atmosphere. But there is another factor at play, and that is El Niño and the Southern Oscillation, or ENSO. This is the strongest year-to-year fluctuation of the climate system on the planet. It's a natural variation of the climate system that's been occurring for millions of years. The warm phase of El Nino we refer to as the warm phase of ENSO we refer to as El Nino, and the cold phase La Nina. And so the way an El Nino develops is the winds in the Western Pacific weaken. That allows the Western Pacific worm pool to migrate eastward. The thermocline flattens out, and that makes it harder to upwell water from the cold interior ocean up to the surface. And so the equatorial band warms all along the equator from the coast of South America out to near the international dateline. And because of that warming in the Central Pacific, the rainfall that's normally found over the Western Pacific migrates eastward, and the winds continue to weaken. And so the ocean and the atmosphere become locked in a positive feedback loop that amplifies initial warm sea surface temperature anomalies to grow into large El Nino events. So actually the shift in these precipitation patterns represent shifts in the sources of tropospheric heating, because when moisture condenses out of the atmosphere and rain occurs, it releases a tremendous amount of heat into the atmosphere. And this heat release at different locations drives far-field teleconnections to the higher latitudes, leaving a global fingerprint of El Nino and La Nina on patterns of weather variability. Typically, El Nino and La Nina peak in the boreal winter season, December through February. And this pattern here represents shifts in the probability for droughts, floods, heat waves, severe tropical storms, and other extreme events in various parts of the globe. And the pattern for El Nino is shown on top, and for La Nina on the bottom. They're roughly opposite. But I've mentioned three places where some unusual weather patterns have occurred this past year. One where I live in the Pacific Northwest, where it has been unusually warm, the dry Amazon River Basin, and the heavy rainfalls and flooding in equatorial East Africa. Now, here's an index that a commonly used index that we use to characterize ENSO cycle variability. It's called Niño 3.4. It's a large areal average of deviations from normal of sea surface temperature in the Central Pacific, where the atmosphere is particularly sensitive to changes in underlying sea surface temperature variations. And the red peaks in this time series going back to 1980 are the El Nino events, and the blue troughs, La Nina events. And you can see the three big El Ninos of the last 40 years, 1982-83, 1997-98, and 2015-16. And then right at the end of the record here is our 2023 to 2024 El Nino. It is not as big as the three extreme events shown earlier from 82-83 to 2015-16, but it's still very strong. The La Nina events are shown by the blue troughs, and you see an asymmetry in the ENSO cycle. The big El Ninos tend to be bigger, but La Ninas tend to last longer. And in fact, right before this strong El Nino, we had a triple dip or 3-year La Nina. And well, that was very unusual. They usually don't last 3 years. It's 2 typically at most, but this one lasted 3 years, and we'll have more to say about that. This event peaked in December 2023, and this shows the pattern of sea surface temperature anomalies, rainfall, and winds for that month. You can see the warm anomalies extending all the way across the basin from the coast of South America to near the international dateline. Associated with that are the shifts in precipitation. It's unusually dry in the Western Pacific, Australia, Indonesia, and the Philippines. And that's because the heavy precipitation has migrated eastward into the Central Pacific. You can also see the signature of an equatorward shift of the intertropical convergence zone, moving towards the warm water at the equator, and an equatorward shift of the South Pacific convergence zone in the southern hemisphere, also moving towards the warm water of the equator. The winds are weaker than normal. Easterlies along the surface. We have these westerly wind anomalies at the surface. And we have unusually strong easterly wind anomalies at the 200 hectopascal level. So basically what this shows is that in association with the warm sea surface temperatures, we have a weakening of the Walker circulation and shifts in tropical rainfall. That's at and above the surface. We can look below the surface, and this shows data from the TAU array. And you can compare December 2023, the thermal structure below the surface, with December 2021, which was in the middle of that recent triple dip La Nina. And in 2023, because the trade winds have weakened, the thermocline has flattened out. Oops. The Western Pacific warm pool has migrated eastward, and upwelling is much less efficient now because the thermocline is so deep. So we see warm water in the Eastern Pacific. Compare that with the La Nina, the trade winds are blowing very strong. The thermocline is tilting down to the west. Most of the warm water is out of the picture here and further to the west, and the thermocline is very shallow and upwelling is robust. So going forward in time, we have a series of forecasts. The first successful forecast of El Nino was made in 1986. And since then, about 30 groups worldwide routinely issue ENSO forecasts every month. And these are assembled by the International Research Institute for Climate and Society, the IRI, and put into this plume format. So these are forecasts for Niño 3.4 sea surface temperature anomalies from February 2024 initial conditions. And so there's a time axis down here. Above a ½ degree Celsius, this plus minus ½ degree Celsius is the neutral zone where we would say it's neither El Nino or La Nina. A forecast above that is for El Nino, and a forecast below the neutral zone is for La Nina. And you can see that most of these forecast models are predicting a transition from El Nino to ENSO neutral by April, June of 2024, and then a transition to colder La Nina conditions by the end of the year. And if we look at the precipitation, the global precipitation forecast, you can see what this predicted El Nino would imply in terms of rainfall. So much greater probability for above normal rainfall in the Western Pacific, Australia, Indonesia, and the Philippines, a wet summer monsoon in India, a wet season in the Sahel, and wet conditions in Central America and Northern Brazil. So this, if La Nina does come to pass, it may provide some relief to drought-stricken Amazon River Basin. Okay, so I next want to turn to 3 ways in which ENSO and climate change can interact to influence some of the extremes that we've seen in the past year. And the first is that ENSO affects global mean surface temperatures. We'll look at this in some detail, but basically this first point explains why 2023 is the warmest year on record. The second way in which climate change and ENSO can interact is that climate change amplifies ENSO impacts. And this is basically because climate change is amplifying the hydrologic cycle. It's a warm atmosphere holds more moisture, so it can rain harder. And also droughts become more extreme because soil moisture dries out more quickly. And this is true not just for ENSO, but for weather in general. And it's also true whether or not climate change has affected ENSO amplitudes. The third way in which climate change and ENSO can interact is, in fact, that climate change can boost ENSO amplitudes. And we'll see, in fact, that it does. So we have a situation where climate change is boosting ENSO amplitudes, and it's also boosting the impacts of that more energetic ENSO cycle. And this is likewise contributing to some of the extremes we've seen. So let's take this first point, that ENSO affects global mean surface temperatures. And here I've got a plot of, on the top, the black line is global mean surface temperature. These are monthly values going back to 1980. And on the bottom is a Niño 3.4 sea surface temperature index. Now that global mean surface temperature curve is more or less constantly rising. except that you see there are lots of year-to-year ups and downs. So what causes those ups and downs? Well, it's pretty evident just by looking at this plot that it's the ENSO cycle. We see that when a big El Nino occurs, like in 97, 98, global mean surface temperatures rise. And when a La Nina occurs, global mean surface temperatures fall. You can do a regression analysis of these two curves after detrending the global mean surface temperatures, and you find that about a 1 degree change in Niño 3.4 sea surface temperature leads to about a 1/10 of a degree rise in global mean surface temperatures with a lag of about 2 to 3 months. It takes some time to redistribute the heat that comes out of the tropical Pacific around the globe, and that lag is about 2 to 3 months. So how is it that ENSO affects global mean surface temperatures? On the right here, it shows those little schematics that I showed earlier. During an El Nino event, the ocean is losing a tremendous amount of heat through evaporative moisture flux to the atmosphere. And when the moisture condenses, it releases heat into the atmosphere. So there's a transfer of heat from the ocean to the atmosphere during El Nino events. Conversely, during La Nina, the surface temperatures are colder, so there's less evaporation. Also, the skies are clearer over the ocean, and so more shortwave radiation is absorbed into the ocean. And so that's why global mean surface temperatures drop during La Ninas. The atmosphere is losing heat to the ocean where it's being stored below the surface. So with that in mind, you can see why before the recent El Nino in 2023-24, 2016 was the hottest year ever recorded. And that's because we had a rising concentrations of greenhouse gas rising concentrations of greenhouse gases in the atmosphere, and a big El Nino. And this is a headline that says, human activity is to blame. That's because of the relentless rise in greenhouse gases, but El Nino was a factor because it released extra heat into the atmosphere. Well, since 2016, global mean surface temperatures plateaued. And the reason is because we had either unusually cold conditions in the tropical Pacific or one very weak El Nino, but they did not rise very much between 2017 and 2022. So there was this plateau. Basically, the ocean was taking up heat and masking the rise in temperatures that would have occurred because of the increases in greenhouse gas concentrations. So then the big El Nino occurs in 2023, and all the heat that was stored below the surface in the tropical Pacific during that period, especially this triple dip La Nina, came back out and led to new record high global mean surface temperatures. Now, you can see this storage and release of heat in Argo data. This is Argo is an effort to maintain a global array of 3,000 robotic profiling floats measuring temperature and salinity in the upper 2,000 meters to document the oceans, the effect of climate variability and change on the oceans. And so what's shown here on the left is a 20-year time series of globally averaged temperature in the upper 2,000 meters relative to the record length mean. And so you can see there is a trend here, and that trend is represented here, particularly in the upper 400 meters. You can see it's cooler at the beginning of the record. It becomes progressively warmer. And then this huge amount of heat that appears at the end of the record, this is the uptake of heat during the triple dip La Nina from 2020 to 2023. And as that triple dip La Nina ends and El Nino develops, you can see the heat that was absorbed in the ocean starts to come back out. You can see the warming here in the surface layer before it's transferred to the atmosphere. Okay, so that's one way in which the climate change and ENSO interact to affect extremes around the planet. And basically, it's the fact that ENSO can affect global mean surface temperatures. Another way in which climate change and ENSO interact is through the hydrologic cycle. We find that a warmer atmosphere due to climate change, rising temperatures, can hold more moisture. A minimum of a 7% increase in moisture per degree Celsius of warming. And this means it can rain more heavily. So for example, if we take a rainfall, an El Nino related rainfall that would have been severe, the fact that the atmosphere can now hold more moisture means that this rainfall can become extreme, like we observed on the Horn of Africa in late 2023. And likewise, warming trends enhance evapotranspiration over land, so the soil moisture dries out more quickly, and this can turn an El Nino, a severe El Nino related drought like we see in the Amazon, into an extreme drought, just because of the amplification of the hydrologic cycle due to rising greenhouse gases in the atmosphere and warming global temperatures. So that's a second way in which climate change and ENSO can interact to affect extremes. And there's a third way, which is that climate change boosts ENSO event amplitudes. Now, the effect on ENSO impacts happens whether or not there's been any change in ENSO cycle amplitude. It's just because of the amplification of the hydrologic cycle. But it turns out that climate change is also affecting the amplitude of ENSO. Now, much of the work that scientists have been working on this problem for nearly 40 years. And I would say much of the progress has come in the past decade through the work of Wenju Chai and his colleagues, of whom I am one. And Chai has led the publication of several papers over the past 10 years that they're forward-looking. They're looking at the question of how will climate change affect ENSO in the coming century. And the answer is very likely. It's very likely that extreme El Nino events will double in frequency by the end of the 21st century as compared to today. But this is forward-looking research. And the reason why we have done that is because greenhouse gas concentrations at the end of the 21st century will be much higher than they are today. And so it's much easier to see the force signal emerge from a background of a very energetic, naturally varying ENSO cycle. A more subtle question is whether climate change has affected ENSO already. I mean, are we feeling the impacts of climate change on ENSO cycle variations today? And I want to walk you through some of the arguments that we made in a paper that came out just last year addressing this question. And again, this is a paper led by Chai in Nature Reviews called Anthropogenic Impacts on 20th Century ENSO Variability Changes. And what's shown on the left is the instrumental record between 1900 and 2020. And this is from one data set. It's the HAD-I-SST. And if you look at this data set and you split it up into two periods, one after 1960 and one before 1960, you get the sense that ENSO cycle variability is more amplified in the latter half of the record compared to the first half of the record. Now, there are half a dozen century-long temperature records besides HAD-ISST here. And so we took all of those and we split them up into pre-1960 and post-1960. And you can see all of these data sets show an amplified ENSO cycle in the more recent 60-year period compared to the earlier 60-year period. And here's the multi-product ensemble mean. So there's about a 10 to 20% amplitude increase across all these data sets. But the issue is that this most recent period is the best sampled period in the climate record. We've got satellites, we've got a whole variety of modern measurement systems in the ocean that are giving us very high accurate estimates of sea surface temperature. If you go back before 1960, we really had to rely only on merchant vessels traversing commercial trade routes And so there were large gaps in space where these data were collected, and there were large gaps in time because the ships would only transit every few weeks to few months. And data quality was poorer. And so, there's a question when you look at the instrumental record, are you really seeing changes in ENSO cycle variability, or are you seeing changes in the way that the SST measurements were measured? So we put that aside for a moment. And we can also look at another source of information, which is paleoproxy data. And these are indirect measurements of climate, temperature, or precipitation in some cases that are encoded in various measurements, like from tree rings, from ice cores, from sediment cores, and from coral growth rings. And for ENSO variability, coral growth rings are particularly valuable because they are measured in the region where ENSO develops, and they measure a proxy of sea surface temperature, which is oxygen isotope ratios. And so here's a study from the Line Islands of the Central Pacific, published in 2019, where they took modern corals and they bandpassed the oxygen 18 records in 2 to 7 year time periods. This is the main period range where ENSO variations occur. And they compared the oxygen isotope records at 3 islands to the instrumental Niño 3.4 sea surface temperature record in black. And you can see there's a very high correlation between these coral oxygen isotope records and the observed sea surface temperature variations. And so you can use that as a calibration, and then you can look at fossil corals and compare them to the modern corals. You can compare the oxygen isotope ratios in the fossil corals to those in the modern corals. So here's the modern record. You go back thousands of years now with fossil corals, and you can see that the ENSO variability in this 2 to 7 year period band is much weaker than in the modern coral record. And so these authors conclude that ENSO extremes of the last 50 years are significantly stronger than those in the pre-industrial era. And this is consistent with some other paleoclimate studies as well. But there are some caveats, as there are with the instrumental record, which is that these corals are very limited in their spatial range. There are only a few places where you can collect reliable long-term records. So we're not sampling the entire spatial structure of ENSO events. And furthermore, they are proxies. They are indirect measurements of temperature that may be contaminated by biological, chemical, and other physical factors not related to climate. Nonetheless, like with the instrumental record, they suggest a stronger ENSO cycle. There is a third source of information to help us address this question, and that is climate change models. And these models have been used successfully in climate change research for more than 50 years. They are comprehensive in that they include actively an interacting ocean, atmosphere, land, cryosphere, and in some cases, biosphere components. And so with the biosphere, they become Earth system models. And for some elements, like the radiative balance of the atmosphere and ocean circulation, they're based on first principles, like the Navier-Stokes equation. And so there are a lot of strengths to using these models. They do have limitations, though, and some of the key processes are limited in terms of how well they can be represented by these coarse grids that the equations of motion have to be coded on. And so you have to rely on parameterized physical processes on scales smaller than a grid spacing, like, for example, cloud microphysics or ocean microstructure. And so the combination of sensitivity to spatial resolution and sensitivity to parameterized physics means that oftentimes these models are subject to systematic errors. And so we have to be careful, just like we have to be careful with the proxy, paleoproxies, and the instrumental record, and how we interpret the results of these models. Nonetheless, let's look at some of the model outputs and compared to the historical record. And again, this is the historical record from the HAD ISST split up into after 1960 and before 1960. And these are some model results. Now, these are results from large ensemble simulations. So a single model that's run for many, many times with slightly different initial conditions. And so we chose those large ensembles. There are 7 of them, 7 different models, but had more than 40 members. That means close to 5,000 years of simulated historical runs from 1900 to 2020. And then we could split the model segments in the same way we do with the data into a pre and post 1960. And we find that 5 of the 7 large ensemble simulations produce an increase in the 20th century, late 20th century, early 21st century ENSO variability. And if you make the large ensemble multi-model mean, that is the average of these 7, you get this. And that the period after 1960 is about 10% more active in terms of ENSO than the period before 1960. Now, these large ensembles are really good for reducing the impact of natural ENSO cycle variability, and so that the force signal stands out more clearly. That's the great advantage of using large ensembles. It reduces the influence of natural variability, so you can see the force signal more clearly. There's another way to look at models, and it's called the model democracy method. There are 43 different CMET models. That is a model intercomparison, the climate model intercomparison program models. And not all of them, few of them are only a few of them have these large ensembles, but all of them, you can take one run, 120-year period at random from these 43 models, and you can compare post-1960 of the historical run with pre-1960. And you find that 33 of the 43 models, or 76% of them, show a stronger ENSO cycle in the period after 1960 than before 1960 in these historical runs. And here is the CMET 6 multi-model ensemble mean, again showing about a 10% increase in ENSO amplitude. So we have these 3 threads of evidence then that suggest that the amplitude of the ENSO cycles is larger in the latter part of the 20th century, early 21st century. One more thing that Chai and all did was they took another 60-year period in the future, 2041 to 2100, and they did the same thing. These are from the large ensembles, looked at the ensemble means of this period in the future, and you can see for most of these models, there is a progression. As you add more greenhouse gas to the atmosphere, the amplitude of the ENSO cycle goes up from the early 19th century to the latter part of the 20th century, from the early 20th century to the latter part of the 20th century into the 21st century. So, and we know the reason for why these models are producing a stronger ENSO cycle under greenhouse gas forcing, intensified greenhouse gas forcing. And that's because if you look at the temperature structure along the equator longitudinally as a function of depth, you find that the difference between 1961 to 2020 minus 1901 to 1960 looks very similar in the observations and in the models. It's more pronounced in the models, but the structure is similar. And what the structure is telling us is that the greenhouse gases are warming the surface of the ocean more than they are the interior of the ocean. And so the vertical temperature stratification is increasing. So we're getting a stronger thermocline. And a stronger thermocline, for the same vertical velocity, will produce a larger sea surface temperature variation. And so you can see that for the various models here on the left, this is the change in temperature stratification per degree C of warming in those models. And here is a measure of ENSO cycle amplitude. And so the stronger the ocean stratification, the stronger the ENSO cycle, because the upwelling process is more efficient. And another way of looking at this is just counting the number of strong events, those that exceed 1.5 standard deviations. And so as the amplitude ocean stratification increases, we get more strong El Nino and La Nina events. And so, in answer to the question, has climate change boosted ENSO amplitudes already? The answer is very likely yes. And even though instrumental data by itself, coral paleoproxies by themselves, and climate models by themselves, you might not necessarily agree about any one of those separately, but they all point in the same direction, about a 10% increase amplitude in the ENSO cycle from the early 20th century up to now. And that furthermore, these models, if they are forced with additional greenhouse gases going into 21st century, they will show additional warming. And so the conclusion is that the ENSO cycle, even today, has gotten a boost from climate change. So this brings me to the end. And in summary, 2023 was the warmest year on record, and it was accompanied by an extraordinary number of weather and climate extremes around the world. And we've just illustrated a few of those, but and it's just a small number that I've illustrated. There's many, many more we could have talked about. Climate change is the underlying cause for these extremes. There's no question about that. It's the rising greenhouse gas concentrations in the atmosphere that are causing the planet to warm and producing more extremes. But on top of that, we have an ENSO cycle. And a strong El Nino, like we see in 2023 and 2024, the strong El Nino affected the timing and the intensity and the regionality of these extremes. And that's because ENSO temporarily boosted the global mean surface temperatures so that 2023 was the warmest year on record, not 2022, not 2021, and not 2020, because those were La Nina years. So this extreme in 2023 was keyed to the development of the strong El Nino. And secondly, climate change related warming trends have amplified ENSO regional impacts is simply because of the overall amplification of the hydrologic cycle, amplifying ENSO impacts, regardless of whether there's any change in ENSO amplitudes themselves. But it turns out that climate change has also affected the ENSO cycle and making it stronger today than it was 100 years ago. And so we have a situation where climate change has boosted the amplitude of ENSO variations, making them, for example, the 2023 El Nino, 2023-24 El Nino is stronger than it might have been otherwise without climate change. And in addition to that, its impacts have been amplified by climate change. So we have these cascading effects, these cascading amplification effects that contribute to climate extremes in the past year. And the final point to make is that the records we set this past year will assuredly be broken. More extremes are on the way as greenhouse gas concentrations continue to rise and as ENSO cycle variations continue to strengthen. So with that, I will conclude and take any questions.
Okay, thanks, Mike, for your very wonderful and inspiring talk. Mike introduced the many climate extremes in 2023, includes the warmest year on record and some droughts and floods and marine heat waves in some regions. And he also connected the effect of ENSO and climate change on all these extremes. And he also extended the view from future projection to present and also to past the paleoproxies. So he gave us maybe it's the human effect maybe have emerged in our historical record, right? So I think the talk includes many interesting aspects that we care about. So if you have any questions, you can directly open your microphone to speak it out, or you can also write it down in the text box and I will read it for you. Okay.
Hello, it's Widong here. Can I ask a question?
Sure.
Hi, Mike. Thanks for excellent talk. I just wonder a little bit about a trend associated with some climate. So from the data, from the observation, it seems in the eastern equatorial Pacific Ocean, the upwelling is somewhat not changed too much, or even a stronger upwelling. But in a multimodal ensemble, it seems the upwelling in that part is somewhat declining. So it makes me a little bit confusing.
Right, right. That's a very good question, and it is a confusing issue. What we have observed over the past 40 years is a trend towards a colder eastern tropical Pacific, whereas most of the climate models say there should be a more permanent El Nino-like condition developing in the tropical Pacific. There's a debate about why that discrepancy. I mean, one idea is that there's natural decadal variability that is affecting the eastern tropical Pacific, and that cooling trend that we've seen will eventually reverse and become a warming trend like the climate models suggest. Now, that the climate model ensemble mean shows a permanent El Nino-like condition, but those models, there are individual models that actually show a temporary cooling, and so there is the possibility that what we're seeing in nature is a natural climate variation. Now, the other aspect of this is that the intensity of the upwelling effect doesn't strictly depend on just the sea surface temperature itself. It depends on the upper ocean temperature gradient. So even with a cooling eastern tropical Pacific over the last 40 years, the vertical gradient below the surface is actually increasing. And that's why the upwelling signal can intensify, even if regardless of what the sign of the trend is in the cold tongue region.
Mike, can I have a question?
Sure.
Yeah, actually, I noticed that you said the unsoil amplitude increased by about 10% under global warming. That is due to like external forcing. And I noticed in observation, the increase maybe more than 10%. I saw the amplitude is much larger than the multimodal ensemble. So do you think is it due to the modal bias, or it is due to some natural internal variabilities, such as the unsoil itself have some multi-decadal variation?
Right. So I think what you're referring to, maybe I'll bring it back up here, is this. Can you see that?
Yeah.
That's what you're referring to.
Yeah.
Yeah. Okay. I think some of this increase is due to anthropogenic effects on the ENSO cycle, but I also think some of the increase is due to the change in observing system. We have much better measurements now than we had 100 years ago. And so what you see in this record, my intuition tells me, is a combination of real amplitude change due to rising greenhouse gas concentrations, plus a better measurements observing system in place. So I think the models, skipping ahead, may give us a better measure from that sense of a 10% increase in the amplitude, because we have both the large ensembles that average out the natural variability and the model democracy that averages out the systematic errors between the models, and they both show about 10%. So I think that's maybe the most robust answer. And I should say that 10% doesn't sound like a lot, but what it's doing is it's making the strong events even stronger. And it's like with hurricanes and tropical storms, it's the strongest events that cause the most damage. So that 10% is really having an impact, even though it doesn't sound like a lot when you average across the entire ENSO cycle.
Yeah, Thank you. Yes, maybe the observation has some bias, not model
Yeah,
bias.
I think there's some bias. I think there's definitely some biases built into the changes in the observing system from over 100 years ago to the satellite era today.
Yes. Okay, thank you. Any questions?
Yeah, Mike. So thank you very much for your excellent talk. So I have two questions. The first one, may climate change impact the frequency of El Niño events? First,
excellent question. It seems like the frequency isn't so much affected. It seems like the amplitude is affected more. But we're limited in our ability to address that question just because of the model systematic errors, the shortness of the instrumental record, and so on. But I would say that the frequency range doesn't appear to shift that much. It's still within that 2 to 7 year band.
Okay, so just now you introduced three ways the interaction between climate change and El Nino. Is there another way the climate change can modulate the teleconnection induced by ENSO?
That's another excellent question. And the answer to that is yes. There are some impacts on the teleconnection patterns that we can see even today, which is that there tends to be an eastward shift in, say, the Pacific North American pattern. And so the shifts in the teleconnection patterns can affect the regionality of the impacts in different parts of the globe. So that is another way that climate change can affect ENSO.
Yeah, thank you. Thank you.
Okay, Monxin, you can unmute yourself and speak.
Okay, thank you. Can you hear me? Thank you so much for your nice talk. I actually have a little question: is how to link the large scale circulation or temperature change to the daily scale extreme weather, especially for the frequency of those extreme weather, like the mid-latitude extreme precipitation or heat wave or droughts. Because I feel that this kind of frequency increase cannot be simply explained by the moister atmosphere under global warming. So what is the other factor increase the frequency of extreme weather?
Well, I think there is evidence that extremes have increased in frequency. The extremes in rainfall, for example, are becoming more intense, and extreme droughts are becoming more frequent. So from the point of view of seasonal forecasting, you actually average over all of those events to get a seasonal picture. But the seasonal picture is made up of a collection of individual events. And so I think because the hydrologic cycle is intensifying under climate change, the wet get wetter and the dry get drier. We're seeing more extremes like that, and so the seasonal averages of those are also showing up as more extremes. The timing, and the amplitude of individual events is something that we cannot predict, seasons in advance. But because of the background changes in global temperatures and their impacts on the hydrologic cycle, statistically, we would expect the extremes to be more frequent, and they should project onto seasonal averages.
So do you mean those extreme events that theoretically being more intense? So with the same threshold, we might expect more frequent extreme events.
Yes, okay. Exactly.
Got it. Thank you so much.
There is a question in the text box. It's from Shi Liu, a student of Academy of Future Ocean. He says, thank you for your wonderful presentation. I'm wondering if there is a relationship between ENSO change and the weather whiplash, like the abrupt shifts between wet and dry streams. I think it's a similar question to the former one.
Yeah. So a weather whiplash, was that the expression?
Yes, it is the abrupt shift from one extreme to another extreme, like from wet to dry.
Yes.
Hot.
Yes.
Yeah.
Oh, that's a great question. There is a whiplash in the ENSO cycle. We typically go from a strong, not always, but often we go from a strong El Nino to a strong La Nina. So there's the rebound effect, there's a whiplash effect. And so we may actually see a fairly strong La Nina following this strong El Nino. But there is a whiplash effect in terms of impacts. I mentioned the Horn of Africa, where we had these extreme rainfalls in what's called the short rain season, which is October, November, December, 2 to 3 times the normal rainfall in October and November of 2023 in a region where we expect El Nino to have an impact. In 2020, 21, and 2022, there was extreme drought associated with the triple dip La Nina. So that part of the world experienced a tremendous whiplash. They went from a historic and prolonged drought caused by the triple dip La Nina and amplified by climate change, amplified because of the faster drying of the soil moisture and the enhanced hydrologic cycle, to one where they had extreme rains over a long period of time. So that was clearly weather whiplash due to the combination of climate change and ENSO.
Yeah. Okay. Thank you.
Great question. Thank you.
Any question? Oh, Yang Zhenyu. Yeah, you can.
Okay. Can you hear me, Dr. Dong?
Yeah.
I can, yes.
Good afternoon, dear Professor Mike. I'm Zhenyu Yang and a student studying AFO. I have a simple question. I was just wondering, you have just say 2023 is the hottest year since 1960, and you just say we have a triple dip La Nina and it have a strong heat, concentrated a very strong heat below our surface ocean. And you just tell us that global warming boosted ENSO amplitudes. So I was wondering, we know that the warm water below the surface ocean is the key point of the ENSO. So now we have the strong we have the we have the warm water below the surface, but why 2023 didn't become the strongest ENSO year since 1960, but it is 1997, 1998, or 2060? That's my questions, and I was just wondering that.
Great question. Yes, you're right. Upper ocean heat content is a precondition for El Nino to occur. So you would expect that the more heat stored below the surface, the bigger the follow-on El Nino would be. And then El Nino, one of the consequences of El Nino is it releases that heat back into the atmosphere. So, but we didn't observe the strongest El Nino on record. These are triggered, and once an El Nino is underway, it tends to organize the atmosphere in such a way that you get more westerly wind bursts. So we call it multiplicative or state-dependent noise forcing. But there is a stochastic element to it. And so, one possibility is that, the westerly wind bursts were just not as frequent or as strong for whatever reason. They're a form of weather variability. And they didn't fully ignite the heat content that was stored below the ocean in such a way as we had another major El Nino. One possibility. I don't really know the answer. I think it's a great question and a great research topic.
Yeah, so in summary, El Nino is is a naughty guy that he always like playing hide and seek games with us.
Yes, yes. It has a mind of its own, and we can, you know.
Yeah. Okay, any question? Oh, there is a question in the text box from Sun Yadong. Thanks for the excellent talk. The notion permanent El Nino is very controversial. Do you think it would occur? Permanent.
Yeah, so the background conditions in the tropical Pacific, if you take the ensemble mean of all the CMIT models, the ensemble mean will show a permanent El Nino-like condition developing in the tropical Pacific, you know, by the end of the 21st century. Not all models show that pattern. Some show actually more permanent La Nina-like condition, but most of them show permanent La Nina, permanent El Nino. And so you know, you don't want to trust the models just because they all agree. But there are some theoretical studies that suggest this is what we would expect as well. That you know, we have now a situation, as I mentioned before, where there is a La Nina-like trend over the last 40 years that's developed. And my sense is that that is more a form of natural decadal climate variability, and that with time, we'll see the effects of the greenhouse gases override that, and the tropical Pacific develop a mean state that kind of looks like a permanent El Nino-like condition. But it's still a very active area of research, and not everyone agrees with that you know, position. I mean, there are some people who think that greenhouse gas forcing should force a permanent La Nina-like state in the tropical Pacific, and this is unresolved. I would say the consensus is for more permanent El Nino, but it's not 100%. Mm-hmm. Another great PhD research topic.
Okay. Yeah, another test from Dr. Dong Xiaowang. Yeah, he said.
Hi, Dong Xiao.
Yeah, nice to hear your talk when we are visiting UCSD. And I just heard Earth's temperature will approach 1.5 level in 2033. How about SST? The delayed time.
So you're saying that so is this in the chat?
Yeah, in the text chat. Yeah, you can.
Okay, let me read that question. Okay.
Yeah.
Just heard Earth temperatures will approach 1 point by 2023. About sea surface temperature. Right. Well, I mean, the global mean surface temperature is a combination of land and ocean. The land is heating up faster than the ocean. You know, depending on what baseline you use, I mean, I was showing graphics related to the using a baseline as the 20th century average. And for that, you know, global mean surface temperature in 2023 was 1.18 degrees Celsius above the 20th century average. If you use 1850 to 1900, that's the late 19th century, you get even a bigger change, 1.35 degrees Celsius. And that's a combination of land and ocean. So, you know, the exact time when temperatures, either the ocean or the global mean surface temperatures, combined land and ocean, exceed 1.5 degrees Celsius is an open question. So, I mean, I could believe it's going to be within the next 10 years. As you know, the rise in greenhouse gases is unabated. You know, we continue to emit, and you know, so it's an unknown when we're going to reach that level, and when we're going to reach that level for land and ocean separately. But it's coming soon, and it well may be in the next 10 years.
Yeah, coming soon.
Thank you. Yeah. Thank you, Mark.
Okay, any question? Okay, if not, let's thanks Mike for accepting our invitation and giving us such an inspiring talk. And very welcome you to visit us at the Academy of Future Ocean, or you see in person in the future. And actually hope I could visit you in Seattle soon in the near future. Actually, I saw some photos about cherry blossom on Utah campus. Yeah, just online this week. So yeah, it's very beautiful. I miss you guys very much. So I hope I could visit you soon in the near future. Yeah, and
thank you.
hoping could enjoy the beautiful spring in Seattle. Yeah, and also thanks all the participants for joining us. And they said today there are in total of about 18,000 person online to hear your talk. So thanks everyone. And yeah, okay, thank you. Have a good night, Mike.
Thank you. Have a good day.
Yeah, thank you. Bye.
Bye.